Okay, let's dive into this. We're surrounded by machines every single day, from our cars to the power plants that light up our cities, and we trust them to work. We kind of assume that if every single part is reliable, then the whole machine has to be reliable too. But what if that assumption is actually dangerously wrong?
It's a paradox that engineers have to deal with constantly. How can a system built from components that are individually rock solid suddenly become this fragile, unpredictable thing? That's the core mystery we're going to unravel today. So, to really get to the bottom of this, we have to start with the basic building blocks of any machine, and a number that sounds incredibly safe: 90%. Now, when an engineer talks about reliability, they're not talking about some vague feeling. Nope, they mean a very, very specific number. It's the statistical chance that a part, say a simple bearing, is going to do its job for its entire expected life without breaking down.
For a lot of standard parts, like the bearings we're looking at here, the industry benchmark for reliability is 90%. That sounds great, right? A 9 out of 10 chance of success. You'd probably take those odds. But this is where our story takes a very, very surprising turn.
That comforting 90% figure, well, it's a bit of a Trojan horse. It's hiding a major flaw at the system level that can have absolutely massive consequences. Okay, so let's do a little thought experiment here, based directly on the source material. Imagine a pretty simple machine. It's got just 10 bearings, and every single one of them meets that solid 90% reliability standard. So, what's the reliability of the machine as a whole? And here's where the math gets really weird and kind of counterintuitive. You don't average the reliability of the parts. No way. To find the total system reliability, you have to multiply the individual reliabilities of every single component together. So for our machine with 10 bearings, the math is 0.90 times itself 10 times, or 0.90 to the 10th power. What do you think that number is going to be? Close to 90%? Maybe 80%. Take a guess.
The reliability of our system plummets. It drops to just under 35%. That is a shocking, shocking drop. We went from parts that are 90% reliable to a system that has a 65% chance of failing.
So here's the crucial point. A system is like a chain. It's only as strong as its weakest link. But when you add more and more links, even really strong ones, you're also adding more and more opportunities for one of them to break. And if just one bearing fails, the whole machine can fail. And listen, this isn't just some theoretical math problem. In the real world, a 35% reliability rating isn't just bad, it can be absolutely catastrophic. Just think about the machines where failure carries an immense risk, to human life, or where it involves massive financial loss. We're talking about airplanes, surgical robots, nuclear power plants. In these fields, a 65% chance of failure is completely, utterly unthinkable. So this presents engineers with a huge challenge, right? They can't just use standard off-the-shelf parts. They need a solid method to design and build systems that can achieve reliability of 99%, 99.9%, or even higher. So how in the world do they do it? They can't just cross their fingers and hope for the best. They need a tool, something that lets them almost look into the future and predict when a part is most likely to give out. And the solution is this really powerful statistical method called the Weibull distribution. Don't let the fancy name scare you. You can basically think of it as an engineer's crystal ball. It takes tons of real-world test data about when parts fail and turns it into a predictable model of a component's life. This graph here shows exactly what the Weibull analysis reveals. Okay, so along the bottom, you've got the probability of failure. As you move to the left, that probability gets incredibly small. But look what happens when you follow that curve up. To get that near-zero chance of failure, you have to accept a shorter rated life for the part. Basically, you have to plan on replacing it sooner. It's a trade-off. Absolute certainty in exchange for a shorter planned lifespan.
So understanding this trade-off is one thing, but how do engineers actually use this information to build a safer machine? Because that's the real goal here.
And this isn't just theory, which is what's so cool about it. The source material points out that this model is built on extensive, real-world testing. In this case, it was data from over 2,500 bearings. And all of that data gets boiled down into a practical, powerful formula.
And here it is. This equation, this is the key. It lets an engineer plug in any reliability they want, let's say 99.9%, and it will spit out the required rated life that a bearing must have to meet that incredible standard. It basically turns guesswork into a precise science.
So, the process in the real world is pretty straightforward.
First, the engineer decides exactly how reliable the final machine needs to be. Then, they use this formula to figure out how strong each individual part has to be to hit that goal. And finally, they go out and select parts that meet, or even better, exceed that calculated specification. That is how you build a safe system.
So I think the big takeaway here is that reliability isn't really about the individual parts. It's about the entire system. A single, super strong component means very little on its own. True safety, true reliability, comes from understanding how all the pieces interact and then designing the whole system, not just its parts, for survival.